In this video we're going to look at some examples of calculus used to find maximum and minimum points. For example, we've got a series of questions here and we're going to pick one of these. We're going to pick the second here where we've got f of x equals x cubed minus 12x and we want to find maximum and minimum points. We can first of all calculate the values at the end points of the function. So the value of the function at the lower end point, f minus 5, is minus 65, and at the upper end point is f of 5 equals 65. Now let's look for any interior turning points. So we take the first derivative of the function f prime x, and that's equal to 3x squared minus 12, and we look for values of x at which that's equal to 0. So we look for values of x such that x squared equals 4. There are two values of x that satisfy that, x equals plus or minus 2. Now to identify the nature of those turning points, we take the second derivative of the function. That gives us 6x. So that's positive when x equals 2, so that's a local minimum. And it's negative when x is equal to minus 2, so that's a local maximum. Now we need to compare these with the endpoints to see if these are global maximum or minimum points. So the value of f when x equals 2 is minus 16, and the value of f when x equals minus 2 is equal to plus 16. So we see that these are local minimum maximum points, with the global maximum and minimum points being at the endpoints. Now this information is actually very useful when sketching the function. As you can see here, we can identify the values at the endpoints and we can identify the turning points and use that to sketch the function. Now let's look at another example. Here we want to find only the interior turning points. So we're going to look at the value, the first function here, f of x equals x log x. Now the first derivative here, f prime x equals x multiplied by 1 over x plus log of x multiplied by 1. We've got that using the product rule. We need to find values such that that's equal to 0. So we need to find values such that 1 plus log x equals 0. Now for that to be equal to 0, we need log x equal to minus 1, or using the exponential transformation, x equals e to the power minus 1, or 1 over e, where e is the exponential number. Now to identify the nature of that turning point, we take the second derivative, and that's just 1 over x. So since x is a positive number, it follows that x equals 1 over e corresponds to a local minimum point. Again, it's useful to sketch the function here because that will give us some information about what happens away from that turning point. So if we take the graph of the function here, we see there is a local minimum, approximately 1 over e, but we can see that the function becomes very large as x becomes large.